Okay, the last one, it's pretty lengthy. It comes to the statement, but let's go through it. We have the sphere with radius r1 and charge to q1, the total charge. Take the electric potential to be zero at an infinite distance from the sphere. Uh, okay, then what are the electric field and electric potential at the surface of the sphere? This sphere is now connected by a long thin conducting wire to another sphere of radius r2 that is several meters from the first sphere. Before the connection is made, this second sphere is unchanged. After electrostatic equilibrium has been reached, what are the total charge of each sphere? C, the electric potential at the surface of the sphere. D, electric field at the surface of each sphere. Assume that the amount of the charge of the wire is much less than the charge on each sphere. Okay, let's get started. Okay, this is empty sphere, conductive one, and we just know already that for the electric field outside, for r greater than its radius, it's 1 by 4 pi epsilon q by r squared. At the surface, we just, to get the value of the electric or potential in the exactly in the surface, we just substitute as a r, small r, the capital R, which is value of the radius, and for r1 for this first sphere, yes, and potential of the first sphere will be the value of the integral from the from the just infinity to the value of the radius of the sphere r1, and dependency is 1 by r, and this is very simple because it's the same like for the point charge, that this is like 1 4 pi epsilon 0 by q r1. You could for example immediately put this equation, but you need to describe it, what I said, that to convince someone who will grade your homework or exam. Okay, and now the answer is that E is 1 by 4 pi epsilon 0 q1 by r1 squared. This is the electric field, which is quite simple, and potential is this. And very important thing that for this specific case, when you compare E and V, they are almost the same, but the only difference is this, yes? And in fact, you can say that V is E times R, or E is a V by R. And it means for such a symmetry, for such a situation, you can go back and forth from E to V by dividing, multiplying this by R. Okay, and now the situation is as follows, that there's another similar sphere but with different radius, could be larger, could be smaller, we don't know it, and connected by a conductor on the wire, which will make the potential of both equal. It means that through this wire the excess of charges go to the direction where are no charges. In this case it's this another sphere, and it will be equilibrium, and for very end in fractions of seconds it will be potential of both equal, and we have such a condition. After connection we have potential of first sphere equal to the second one, and because we had limited sorts of charges, the reservoir of charges was first sphere, that q1, the initial value of sorts charges, is equal q1 to plus q2. It means that this redistribute among two spheres, but not equally. We have to calculate how. And after substituting the condition of this is the potential of first sphere, assuming that there is some value of q1 on it after connection, and also some unknown q2 after connection. With common terms we can cancel out, and we end it with such a proportion, and by diagonal multiplying we can find that let's say this q2 times r1 is equal q1 times r2. And now from this equation exactly from this, I can calculate it that Q1 is equal to capital Q1 minus, it goes here, Q2. And eventually I have this equation. And now I am substituting this here, and I can calculate Q2 is equal Q1 minus Q2, this guy divided by this guy, and was multiplied by this R2 by R1. And I'm just multiplying this by this by this, and I got this guy and this guy. And eventually I am ending up with Q2 plus, I'm just, putting terms with small q2 next to each other, and I can calculate, take it as a common term, and out of solve for q2 will gives me such a term, which eventually is r2 times q1 by r1 plus r2. And this is for q2. We already have q2. To have q1, we can substitute this guy to the q1 guy here, and this is what I'm doing. And eventually, after like simple but not very short algebra, I can show that the trick is that I'm substituting 1 here by the same r1 plus 2 divided by r1 plus 2. This is also 1, but that way it's easy to find because this term will cancel out with this term. I'm showing q1 as r1 plus r2. They are very similar. When we summarize them, the only difference is that for q1 is r1, for q2 r2. Now we're having q's, and now either we can assume that wire is disconnected or not. It doesn't matter, in fact, what is happening. We can calculate v1 using the equation, but as a q we substitute q1. And after algebra, we find that one r1 will cancel out with this r1, because r1 will be in the denominator of our q, this guy, and I end up with such a not trivial solution. If it comes to v2, it's like by analogy almost the same, but only difference is that we have r2 and 2 here. And I have very interesting thing. If you compare this guy with this guy, they are exactly the same. The math shows you that the potential are equal. I mean, you already knew this condition because when you connect using two connector conducting wire, two different potentials, they will there's kind of situation that they have to equal in the very end. And this is what intuition can say you immediately, but this math also shows you this. And this is what I stated here. For the last one, I used what I said here, the story that having V, I immediately can have E. But it doesn't work for all situations, but for the sphere it works, and I used this, and what I have, this is the equation describing what is the electric field, how it's changed, how it depends on, in fact, these parameters of these two spheres after connecting them. Okay, that's it, and thank you.